Okay, so it's time to start. Uh, so let me remind you where we are. So last time we talked about sets, right? So and then we look at finite sets and try to count how many elements are inside. So and then we introduce this inclusion-exclusion principle, so that we can count some particular sets, right? Um, so we end with this pigeonhole principle. So this is a property about finite sets, actually. So today the real topic is about infinity. So you'll see that from finite to infinite, the jump was really huge. So it's a huge difference between the property of finite sets and property of infinite sets. So let me finish this pigeonhole principle, the topic on pigeonhole principle, and then we'll see the word of infinity. Okay, so we have seen this slide, so let me read it one more time. So there's a mathematical principle called pigeonhole principle. It says this: suppose I have two natural numbers, m and n. If m is bigger than n, and then any function from a set of m elements to n elements cannot be injected. Well, written in this form is looks abstract, but the name actually comes from this example. So the names comes from, imagine you have m pigeons and you want to distribute, you want to put them into n pigeonholes. But the number of pigeons is strictly bigger than the number of pigeonholes, right? So suppose you have m pigeons and n pigeonholes, and m is bigger than n, and then at least one of the one of the pigeonhole will get more than one pigeon, right? Because no matter how hard you try, some pigeons have to share the same pigeonhole, because you don't have enough space for them to stay in a single room, right? So the principle was quite intuitive. Okay, you'll see that this is a property about finite numbers, because here m and n are natural numbers. So it's a concrete finite number, just like 2020 or 1 million. So it could be a very big number, but it's finite. Okay. I hope the statement is clear to you. Okay. So now I'm going to state some theorems about functions from finite set to finite set. But again, written in this form, it looks maybe a little bit too abstract. So I want to go back to see a picture, and if you understand the picture, you understand what I'm going to say. Okay, so I want to go back to this picture. So this picture actually says what I want to say when the m is 4. Okay, sorry. I'm trying to give you an example. Then this example will illustrate the principles I'm going to say in general. Okay? So now look at this the top picture here. So okay. So I want to say, look at this picture. I have a function from 4 elements to 4 elements. So on the left hand side, I call the 4 elements A, B, C, D. On the right hand side, the 4 elements are labeled 1, 2, 3, 4. So the capital F is a function from A, B, C, D to 1, 2, 3, 4. So it's a function from 4 elements to 4 elements. Okay? So now first let's assume F is not onto. F is not surjective. Right? What does it mean? So maybe I write it down. Okay, so now I have the pen is available. So first let's think of it. So question 1 for you. Think of, so suppose F is not surjective. Let's study whether F can be injective. Right? So okay, suppose F is not surjective. So this is the picture. Right? Here I miss 4. F didn't hit some number. It's not surjective. Right? So in other words, F start from 4 points, but if you look at image, because you can't hit 4, you have only 3 places to choose. Right? So it's like I have 4 pigeons, but only 3 pigeonholes. So you can imagine that at least 2 pigeons will share the same pigeonhole. So therefore, the function f is not injective as well, right? So this picture says, okay, so it's not question 1. So what I want to say is, suppose f is not surjective, then f is not injective either, right? Injective. I hope this is clear in this particular example, right? You see the so it's from 4 elements to 4 elements. If it's not surjective, you'll miss some point. It could be 4, could be something else, right? So if you miss some point, we are in the situation I have 4 pigeons, but I only have 3 pigeonholes. So some of the pigeons will share 1 pigeonhole, which will demonstrate the function is not injective. I hope I'm clear about this. Okay. Now think of the similar question. So suppose f is not injective. Right? So imagine that we now have a situation f is not injective. So for example, the same picture, like 2 of them will hit the same target, right? For example, FA and FB hit O equal to 3, O map to 3, right? Okay, in this situation, I want to convince you F cannot be surjective. You see, here I have 2 points share. Okay, let's say 2 pigeons share the same hole, right? Number 3. Now I only have 2 pigeons left, right? So if A and B share the room number 3, and then I have two pigeons C and D left. But now on the right hand side I have three pigeonholes, right? So I have 2 pigeons, 3 pigeonholes. Again, I cannot fill out all of them. One of them has to be empty, right? So if f is not injective, then this picture shows f cannot be surjective as well. Okay, so the conclusion is, if f is not injective, then f is not surjective. Okay, so this is the picture, right? So the picture apply to 4 elements, because 4 elements is easy to see, to draw, right? Now the slides I'm going to show you in a moment just change 4 to m. Okay, so I will consider a function from m elements to m elements. I want to do the same reasoning. I'll say, if it's not injective, then it is not surjective. If it's not surjective, then it's not injective. So therefore, the injective surjective always come together. If you are not injective, then you are not surjective. If you are not surjective, now right. So I hope the picture is clear to you. So then the slides will be the abstract version, and it's probably less readable. Okay, so let's try. Okay, so I want to do the same thing. Okay, so I want to say that the injective and surjective always happen together. If they fail, they fail together. If they hold together, right? Okay, so here is so we consider A and B. So they are A and B are a finite set of same number of elements. Let's assume that A and B are sets of m elements, right? So in the example, it was 4, but now let's imagine we have m elements. So the claim says if f is injective, then it is surjective. Well, just now the argument I give you is if it's not this, then not that. But you know this statement is the same as is contrapositive. Right? This is the same as if f is not surjective, then f is not injective. Right? So I'm doing the same thing. Okay. So okay. So now if you imagine that the m elements are pigeons, the elements in A are pigeons, the elements in B are pigeonholes, and then so this thing says suppose A and B, suppose there's no two pigeons sharing the same pigeonhole, and then all pigeonholes are occupied. Right? So because if you miss something, sorry. So let me write it. So first, I want to remind you that this is the same. This is the conclusion. This is equivalent to is contrapositive. Contrapositive means this: if f is not surjective, then f is not injective. Right? Is it clear? So close the bracket. So the conclusion says if f is injective, then f is surjective. This is like P implies Q. We know that this is equivalent to not Q imply not P. So not Q means f is not surjective, and then not P says f is not injective. So it's the same, right? Now, so because there are new people comes in, so this is indeed the same picture, right? So this says if it's not surjective, if you miss one of the pigeonholes, and then some of them will share. They'll share the same some pigeonholes, right? So indeed, this is a okay. So this is the abstract version of what we have seen, right? What we have seen is m equal 4. Now I state it for m. It's just like that, right? The reasoning is the same, but written in mathematics it looks less readable. Okay, so let's see. So what's the reasoning? So if not, and then m must miss some points in B. F must miss some point in B, right? Because if it's not surjective, then some point was not hit, right? F must meet some, in the picture it missed number 4. Okay, so the range of F has less than m. In the example is three elements, right? So now you have from 4 elements to 3 elements. You cannot be injective because this is pigeonhole principle, right? So this is the proof. Okay. Now this is the other part. I'm saying if it's surjective, then it is injective. Then you can imagine that the contrapositive says if it's not injective, then it's not surjective, right? It's the same thing. I guess I won't repeat the argument. The picture of m equal 4, I think, is convincing enough for you. So forgive me to not read this. Okay. These are too mathematical. Okay. So combine the statement I just said. Actually, what's happening, we can summarize it in a theorem. The theorem says, suppose I have two finite sets, A and B, and they have the same number of elements. Both have m elements, let's assume. And then any function from A to B, if it is injective, then it is surjective. And this is if and only if, right? The other way around. If it's surjective, then it's injective. So it's injective and surjective are the same thing for finite sets. Is it? Let me read it one more time. Right? So here we have two finite sets of the same size. Right? They all have 4 elements, for example. Now, if you consider any function, so the function, if you say the function is injective, then it automatically surjective. If the function is surjective, it automatically injective. So injective and surjective are more or less the same thing. You can't separate them. Okay? I hope this is all right, right? Okay. Now I put the condition finite in red. So this only applies for finite sets. In a moment, immediately you'll see counterexamples for infinite sets. Okay. So you'll see this is not true. Otherwise, we will not have two concepts. Right? If injective surjective are the same concept, we don't invent two concepts for the same thing. Okay. Okay. So now pigeonhole principle have lots of applications. So especially when you try to do some counting. So for example, here, there are 2 examples I'm going to give you. So one example says this. So if you are at a reception or at a party attended by more than 367 guests, right? So can you be sure that there will be at least 2 persons with the same birthday? Okay, so imagine the guests are like pigeons, right? So you have this many pigeons, and then the day they were born was like pigeonhole. So the 1st of January is one of the pigeonhole, 2nd January is another one. So the whole year, it's okay. Usually it's 365, right? But in some leap year, you could have 366. But no matter what happened, it's less than this number, right? So you have imagine you have 367 pigeons. You have at most 366 pigeonholes. So at least two pigeons will share the same pigeonhole. In other words, 2 guests will share the same birthday, right? So this is here, right? Now there's another example. It's more or less the same. So a dating agency requires each of its clients to answer a questionnaire consisting of 10 questions with yes/no answers. Okay. Now there are 525 male and 500 female clients. Can you be sure that there will be 2 questionnaires with identical answers? Identical answers means, for example, person A answered yes, yes, no. So first 2 yes, the other are no. And then person B with identical answers will be also the first 2 questions are yes, the other 8 are no, right? So they give for the same question, give the same answer. Now, okay, so the answer for the question is yes. Well, because it's the same application of pigeonhole principle. Because you have how many questionnaires? So you have, if you add these, you get 1,025, right, questionnaires. Now, how many different answers can you have? So for the question 1, you have 2 answers. Question 2, you have another 2 answers. So the combination will be 2 times 2. You have 4 different ways for the first 2 questions. And then if you have 3 questions, is 2 times 2 times 2, right? So altogether, you have 2 to the power of 10 possible answers. Okay? So the 2 to the power of 10 is 1024. So therefore, you have more, again, this is application of pigeonhole principle. So at least 2 persons will have identical answers. It doesn't guarantee that the 2 persons is 1 boy, 1 girl, right? Because you don't have that information. Okay. Is this all right? So this is another application. Okay, so now with this, we catch up with, we finish the lecture 5. So now I'm going to, let's look at the new lecture 6. Okay, so the topic is about infinity, okay, or the infinite. Okay, so this is probably the most abstract lecture in the whole semester. Okay, but I like this topic because you need mathematics to understand it. Okay, so our course is called Living with Mathematics, but this part is far away from us, right? Because in real life, probably there's no infinite things. Everything was finite, right? So this is today's lecture is special. Is inside pure mathematics in a very abstract realm, right? It's not about counting, not about calculation. It's about thinking. Okay. Okay. So let's see whether I'm able to tell you some interesting facts about infinity. Okay. Okay. So there are the outline are about these things. So one is about the basic concept. Right. To understand infinity, you have to understand something else. Right. So those are the things. But we have done the preparation. The only thing you need to know is about the function being injective, surjective, or bijective. That's the preparation. And then we look at the size of natural numbers, and we also look at the size of real numbers. Okay, so you can think of it. Are they have the same size? And then there is an interesting mathematical problem called the continuum hypothesis. This problem brings lots of, it's a very challenging mathematical problem. And it is also a very, very, very challenging philosophical problem. So, I'll tell you what is the impact of this continuum hypothesis to the philosophy of mathematics. Okay. All right. So first, let me quote Hilbert. Right. Last time we mentioned his name. So he is probably one of the most, one of the greatest mathematicians of all time. Right. Okay. So he, in 1926, he wrote a long article called "On the Infinite." So this is from the quote is from that long article. Okay. So Hilbert says, okay, so the definite clarification of the nature of the infinity, instead of pertaining just to the sphere of specialized scientific interest, is needed for the dignity of the human intellect itself. Okay. Now, why do I put the quote here? Why did he make this quote? Remember, last time he mentioned lots of paradoxes, right? So in the early 20th century, there are mathematical problems, right? There was Russell's paradox, and some other paradoxes. So people believe the source of the paradox is because we went too abstract. So we went to somewhere we don't have clear ideas. So the infinity is one of them. So in mathematics, you not only you see the simple infinity, you see very complicated infinite objects. So it was so confusing, so abstract that the human being probably overreach, right? So the infinity is too complicated. We went too far, right? So some people suggest we should stay at the places we are clear. We have a clear idea. So what are the things we have clear idea? Finite, right? So Hilbert, he did not agree with that idea. So he was saying he's trying to give clarification of infinity, right? So he's trying to show people that mathematics is safe, and infinity, we can use the idea of infinity, and it is important, right? So it's not only it's important for mathematicians, for some specialized scientific interest, it is also for everyone, for every human being. Okay, so I choose this to try to give you motivation. Okay, so we just finished the pigeonhole principle, right? So pigeonhole principle is about finite sets, right? So it says, suppose we have a function from, just now I say m, from two sets with m numbers. Now I change it to n. It doesn't matter. So suppose I have a function from two finite sets from a to b, where both a and b has n elements, right? And then being injective is the same as being surjective, right? So I repeat this, I don't know how many times already in the past 20 minutes. Okay, now what happens if the set is infinite? Is it still true, right? So the answer is no. There are lots of examples. For example, let's consider a function from natural numbers to natural numbers. So natural number is a typical example of infinite set, right? Because there are infinitely many natural numbers. Okay, so let's consider a function from n to n, defined by multiply by 2. Right? For example, f1 is 2, f3 is 6, right? f5 is 10. Right? Now this f is injective. Different points send to different points because, right? So if x is different from y, then 2x is different from 2y, right? But this is not surjective because it always hits even numbers. This function miss all odd numbers. So therefore, it's not surjective at all. There are lots of holes, right? So this is an example of being injective but not surjective. It's easy to give an example. Some function is surjective but not injective. Okay, so let me emphasize the pigeonhole principles only holds for finite sets, because once you enter the realm of infinity, things are different. Okay, so that's okay. So now let's pretend we don't know anything about infinite sets. I know some of you are taken from the CS 1231, so you definitely have certain knowledge about infinite sets. Let's pretend we start from scratch. Right? We don't know anything. So can we count infinite sets? So that's the question. So first, we can count finite sets, right? So we can count the number of elements in a finite set, and we can also compare the size of two finite sets, right? So some trivial examples. This set, the set of 0, 1, there are two elements, so the size is 2, right? So we write the modulus, or you use the absolute value notation to denote the size of the set. So the size of the set 0, 1 is 2. Okay? And then it's easy, the set of ABC has 3 elements, right? So the size is 3. Now you can compare. So which set has more elements? Well, obviously ABC, it has, the size is larger. Right? So for finite sets, because you can count, is clear. Okay? Now how about infinite set? So the question is, do infinite sets have sizes? Right? Does it make sense even to talk about it? So can we compare any two infinite sets, like natural numbers and real numbers? Can we say which one has more elements? Okay. Okay. So this is the introduction for set theory. Set theory was invented by him, by Cantor, Georg Cantor. That's his picture. Okay, so now how do we, so he comes out with this idea, right? So how do we compare two infinite sets? So his idea is two sets have the same size if you can match their elements in a nice way, right? If there is a perfect matching between the elements. Well, okay, so there are also examples, right? So sometimes you don't need to count the objects. Then you know they have the same size. So, well, there are lots of informal examples, right? So typically people will say that, okay, the number of noses in the auditorium is the same as the number of mouses, right? Because, well, each person only have one mouth, one nose. So they're the same. Right? So you don't need to count. I don't need to count how many people in the audience. Then I know the set of noses have the same size as the set of mouths. Right? Mouses. Okay. Or suppose it's a full house, right? Then I know the number of people is the same as the number of chairs. I don't need to count how many chairs. As long as, I mean, it's full house and no people sitting on the stairs, I know that they have the same size. So as long as I can match the the elements of the two sets, I know they have the same size, right? I guess you, if you read some popular books, they always use this example. They will say that in some remote island, maybe somewhere, and there's a tribe. So the people in the tribe can only count up to 3, something like this, right? So if they count, if beyond 3, they will say many, right? Okay, so now imagine you give them two. How to say? You play Go, right? You know that sometimes you have, you give them two small baskets. One contains black stones, the other contains white stones. So you ask the people in the tribe, do I have more white stone than the black stone, or vice versa? Can I compare the size of the black stones and the white stones? Right. So because they cannot count beyond 3. For them, just count how many stones in the bag is not a solution, because they can only count up to 3, right? So the challenge for you is, can you help them to decide, do I have more white stones than black, or vice versa, or they have the same, I have the same number of white stones as black stones. Okay, so the answer is, again, use this idea. Use the matching the elements. So the answer for the tribe people is, you take out one white stone, and then take out one black stone. Maybe throw it in the sea or something, and then take the next one, right? So until you exhaust one of the bags. If you exhaust them at the same time, then you know they have the same amount of stones. If you finish the white first, you know you have more black. Right? If you finish black first, then you have more white. So without counting by matching the elements, you can tell which one has a larger size, right? So these are the informal examples. So now here, the word perfect matching is not mathematical. We can give a more mathematical definition, right? So the perfect matching means a bijection. Okay. So the knowledge we learn about functions is useful. Okay. So the definition says, okay, so suppose I have two sets, A and B. We say that A and B have the same, okay, the fancy word for size is called cardinality. Okay, have the same cardinality written in this form. The size of A is the same as size of B. The cardinality of A is the same as cardinality of B. If there is a bijection from A onto B, right, if you can match the elements in a nice way, then they have the same size. Okay. Now, by the way, this definition works for finite set too. The example I give you for the black stone and white stone, they are finite sets, but you can use this method to compare their size, right? Well, Gödel gave a reasoning. So why, if we match the two sets, then they are the same. They have the same size. So he gave a okay. So he gave an example like this. Imagine that you have A and B, right? So you can match the elements between A and B. Maybe it's not drawing, but okay. So maybe you have a set A. So A consists of things, I don't know, in various shapes like triangles. Okay. So A has lots of things, and B have things, they are round objects. I don't know, I cannot draw it. There are different objects, right? But the elements in A are like triangular shape. Elements in B are round shape. Okay. Now maybe they have different color or something. Now suppose you can match them. Right? Suppose you can match them. I want to convince you that they have the same size. So this is just an example. Don't take it too seriously. So Gödel says, imagine that these things are made of, I don't know, soft, I don't know, rubber or some soft things, mud. So you can change the shape of the triangle into round shape. Right? So you just mimic, how to say, for example, you look at the first pair, and then somehow you massage the triangle so that it looks like the corresponding circle, round shaped things. Okay. Now suppose you have a color, you also recolor the triangle with the same color as the matching object. Right? So you do it for every element. And then you have exactly same set, right? Because suppose you can massage the shape. Now you massage the first one into this round shape. You massage the second one into just like the second element in B. You make it the same, right? So now in front of you have two sets, but they are exactly the same elements, because you can't tell the difference because you massage the elements, right? So if they are the same elements, they certainly have the same number of elements, right? They have the same size. But when you massage each individual element, you didn't change the size of A at all. You just you only change the shape or the color of the element. You didn't change the number. You didn't take two numbers and put them into one, right? You didn't split one into two. So you didn't change the number. You just changed the physical shape of the objects, right? So anyway, so there are reasons to justify this. But however, these reasons are not mathematical. So I can give you reasons to justify things in this way. Clever people may give you reasons to justify the opposite things, right? So now let's look at the real story. These things happen in real life. So Galileo, is a famous physicist or astronomer. So he was. So he discovered in his book. He mentioned this example. So he looked at this the set 1, 2, 3. He didn't use the word set, but so this is a modern phrasing of his idea. So he looked at the numbers 1, 2, 3, etc., and he looked at the squares, the perfect squares. So 1 and 4, 4 is 2 square, 9 is 3 square. So he compared these two sets. Okay. So now they have the same cardinality based on our definition, because there's a bijection, right? I take n equal fn equal n squared. I have bijection. I match them perfectly. Okay. But Galileo says, okay, it cannot be denied that there are as many squares, the perfect squares, as there are numbers, because you can match them, right? The reasoning I gave you, if you can match them, they are the same, right? So you can do this: 1 match to 1, 2 match to 2 square, 3 match to 3 square, and so on. You can do this matching. But okay, so if you look at this way, they are of the same size. But this is wrong, according to Galileo, right? Yet the outside we said there are many more numbers than squares, because this is a proper subset. You see that every squares are in the collection of natural numbers, right? So there are more numbers than squares, since the larger portion of them are not squares, right? You see here, not only the 4 and 9 appear here, there are much more numbers, like 2 and 3. They are in the origin. They are in this set, but not in the squares, right? And Galileo also observed that as you move, when you look at larger and larger numbers, the gap are getting bigger and bigger, right? So the squares getting sparse, more and more sparse, right? So the lesson for Galileo is the infinity is complicated. It doesn't make sense to talk about size, because look at this strange example. You can match a set with, you can match a set with its proper subsets, right? So now, what stops Galileo to be counter, to have this new idea, is because Galileo believed like Euclid, from Greek times, right? People agree with this principle, which says the whole is greater than the part. Right? If you look at the piece of pie, right? So somehow the whole pie is definitely bigger than any slice of the pies, right? So this is an old belief. And Euclid, the famous geometer in the Greek times, he states this as an axiom. He says this is definitely true. The whole is bigger than the part, right? So if you believe Euclid, well, the set of squares is part of the whole, which is a set of the positive natural numbers. So therefore, the whole is bigger than parts. So this set should be bigger than this, right? So that was Galileo's reasoning, and it's also reasonable, right? So what's the summary? The summary is we have two old principles. I mean, we have two ways of looking at things. One is if we can match, then they have the same size. So this is one. This is observation number 1. Observation number 2 says the whole is bigger than parts. The two things are contradictory, right? You cannot You cannot have them both. Which one do you give up? Galileo gave up the first one. Right? He says the world of infinity is too complicated. We belong to the God. Right? Human beings we cannot work on infinity because the example like this. Right? But Cantor made this revolution because he gave up the second part. And then he get an interesting theory about infinity. So we are going to see what's happening for Cantor. Is this okay? So now first let me give you some examples. So for example, here based on, so now we take Cantor's definition as a good definition. We give up the idea of a whole is bigger than parts, right? So this is we are going to see many examples that for infinite set, a proper subset can have the same size as the original set, right? So for example, this, if you not only look at squares, you look at the even numbers. So the size of natural numbers is the same as the size of even numbers, because if you multiply by 2, you get a bijection between natural numbers and even numbers, right? So therefore, they have the same size. Now, Hilbert is the same Hilbert. There is usually people use this to illustrate the idea. So the story, the imagined story is you have a hotel, right? So the hotel can hold certain people. So now on certain night, maybe tonight, all rooms are occupied. Okay. Now there's a new person coming, like here, the new person coming. So Hilbert, sorry. So the funny thing about Hilbert Hotel is Hilbert Hotel has infinitely many rooms. If it has finite room like PGP, suppose it's full, right? So you have another new person, you can't squeeze in, right? But Hilbert Hotel has infinitely many rooms. So Hilbert make this arrangement, right? So everybody move to, suppose you are living in number 1, move to number 2. So you suppose you are living in number 2, you move to number 3, the room number 3. So if your current room number is n, just move to n plus 1. By doing this, everybody shift, right? I mean, the cartoon says everybody look like Hilbert, right? Everybody shift to the next room. And suddenly, the first room is empty. So the newcomer can stay inside the first room. Right? This is strange. This is counterintuitive, right? Okay, now the story didn't end here. So you have, imagine that you still have this Hilbert Hotel. It is no vacancy. It is fully occupied at this moment. Now suddenly you have the same number of guests, right? You have these long queue. You have infinitely many guests arriving, waiting for the. They want to stay somewhere. Right? Again, in PGP, this is impossible. You cannot do it. But this is Hilbert Hotel. So Hilbert will say, now, you don't move to your next room. Instead, you do this. You move to the room which doubles your number. Okay. Suppose you are in number 1. Now you are in number 1. Go to number 2. If you are in number 2, go to the room number which is 2 times 2, which is, you go to number 4. If you are in number 3, you go to 2 times 3. You go to 6. Right? So these people already occupy the room. They have to do something, but not too bad, right? You just move to the, suppose you are in n, you just move to a room of room number 2n, 2 times n. Now, by doing this, suddenly the room with odd numbers are empty. So the infinite many new guests can be slotted into the room with odd numbers. Right? So this is a funny Hilbert Hotel story. Okay. Anyway, so I hope the idea is clear. It's a strange hotel, but the word of infinity is strange. Now we are going to see a couple more examples of this funny, how to say. We are going to see a few more sets. One is a proper subset of the other, but yet they have the same cardinality. They have the same size. Okay, so the first thing I want to convince you is the set of natural numbers has the same size as a set of integers. Although on picture the set of natural numbers only take half of the line, right? The integer can go both positive and negative, but the set of natural numbers can only go to positive. It misses all the negative numbers. It's like the Hilbert Hotel, right? So, okay. So I want to convince you this. So the mathematical way to show this is I have to define a bijection. I have to match the elements of integers with the elements of natural numbers. If I can have a bijection, I win. Right? I convince you. Okay, so the idea is very simple, right? It's like the Hilbert Hotel. So here I have lots of negative numbers. I want to slot in. I want to match the negative numbers with some positive numbers. So what can I do? So first, inside natural numbers, I can use even numbers to match all the non-negative parts of Z. Just now we showed the set of the set of natural numbers has the same size as even numbers. So I can use even numbers to absorb the positive part of integers. And then I still have the odd numbers empty. So I'll put the negative part of integers to the odd numbers. Right? So that's the idea. Now the definition looks a bit mathematical. So this is the way you do it. So I define a function f from n to z, defined this way. So if n is an even number, I'm going to divide it by 2. So I'm going to give you I'm going to return you a positive integer. Right? For example, n is 6, then fn is 3. Okay. Now for the odd numbers, I'm going to return you a negative number. Right? So the way I return you is this. For example, n is 3, right? So 3 plus 1 is 4, so I'll give you negative 2. Right? So f3 is negative 2. So this is the definition. And then we claim that this is a bijection. Okay. I think next slide I give you a proof, but I guess let's don't be bothered. But so you can check the function I define this way is indeed injection and surjection. I'll probably leave the reading to you. It's not hard. Okay. So let me skip the proof. So now the next target my next target is to convince you the natural numbers not only they have the same size as integers, they actually have same size as rational numbers. But rational numbers, it seems lots more rational numbers than natural numbers, because, for example, 1/3, which is 0.3333 all the way, is a rational number, right? So between any two natural numbers, there are lots of rational numbers. So between 1 and 2, you have 1.1, 1.2, 1.3, and 1.33, and 0.333. So you have so many more rational numbers, it seems. But I want to convince you that the size of natural numbers actually is the same as the size of rational numbers. So this is more striking, is more strange, right? Now before that, I need to do some preparation. I need to use several middle steps, right? So maybe I'll introduce some concept and then we take a break and then come back. So let me remind you this Cartesian product. So let A and B be sets. The product or Cartesian product of A and B is a set of all ordered pairs whose first component comes from capital A, the second component comes from capital B. So in other words, the product collect all the pairs. So this notation denotes the pairs of small a and small b, where the first component, small a, comes from the first set, capital A. The second component, small b, comes from capital B. Right? So I think you have studied R2, for example, right? So R2 is an example of the real number across real number, right? So okay, so the Cartesian, the name comes from Descartes. Descartes is Descartes. So this is the real name. Okay, so some examples. Suppose capital A is 1, 2, 3, capital B is A and B. Now A times B, okay, so you take pairs where the first component is a number, the second component is a letter. So you try all these possibilities. So you get A times B, which is different from B times A. So that's why it's ordered pairs, right? So the B times A, the first component comes from B, which is a letter. The second component comes from A, which is a number, right? So they are not equal. Okay, so if A equal B, then we just write A squared. A squared is A times A. Right? Now, in JC or in linear algebra, you know R2 is the Euclidean plane. Right? Our plane can be, you can put coordinates, you can put, right? And Z squared is a set of integers, grid points on the plane. Right? Z2 is 1, 1, 1, 2, so they are the integral points on the Euclidean plane. Okay, so okay, so let's take a short break. After that, we see some heavy mathematics. Okay, so let's continue the examples, right? So I'm heading towards the size of natural number is the same as size of rational numbers. Before that, I need to do some preparation. So first, I introduce this Cartesian product. The middle step is this. I'm going to convince you the size of natural numbers, n, is the same as the size of the Cartesian product, n cross n. Okay. So, well, there are mathematical proofs, like we need a bijection. So define f in this way, and it turns out to be a bijection. So I will skip the proof. Okay. Now I want to show you a pictorial proof. So okay. So maybe I can use the PDF. I can draw a new picture. Okay, what I want to show you is, remember that, okay, we are going to see this picture in a moment, but I want to convince you this n cross n can be matched, right? So can be sort of matched with n. This is my job, okay? So what is n cross n? So I have lots of points here. Okay, so although n is not continuous, but when I draw a picture, I can only draw a continuous line. So forgive me to draw this to represent n. So since I start from 0, so the n cross n has an element 0, 0, right? And then x equal 1, y equals 0. I have 1, 0. And here I have 2, 0, and so on and so forth. Okay. Now there are lots of things because, okay, so here I have 0, 1, right? The x coordinate is 0, but the height, the y coordinate is 1. So I can also have 0, 2, right? Now here I have 1, 1. Both the x-axis, x coordinates and y coordinates are 1. And then I can have, maybe I draw one more. So here this point is 1, 2, right? So these, okay, let me emphasize, these bullet points are the points in n cross n. Okay, so I draw a couple more. Okay, so these, the grid, right? So the integral points here, the bullet points on this picture, these are n cross n. Now I want to match them with n. So I want to label them in a linear order. I want to somehow massage this picture, two-dimensional picture, so that all the bullet points are placed on a line. If I can do that, well, I'm done, right? So the way I'm going to do it is I'm going to do this. Is similar to this picture. I'm going to do this zigzag way. So I'm going to draw a line here in this way. So the line. So I start from this corner. I go up 1 unit, and then I come to take care of this 1, 0. Okay, then my line, I put my thread back to the y-axis. I get here, and then I go down in a diagonal fashion. And then after I hit x-axis, I go up again, and then go down by the diagonal. And then I go up again to somewhere here, and then go down by diagonal. So you see the red things, imagine the red are made of silk or thread. The red things, maybe they are longer, they take longer, they are longer than the black line, but the thread actually is a straight line. I mean, you can imagine you can pull this side, right? You can pull this side to this way, then all the red become, all the zigzag becomes straight. So actually you get a straight line. So you can label this as your 0, this is 1, this is 2, and 3, 4, 5, 6, 7, 8. So you can relabel the bullet points on the plane in a way as if they are on a line, right? So this is a way of showing I can match the bullet points on the plane with the natural numbers. Actually, you can write down you can write a function. I think if you have taken CS1231, you've probably seen this. But here I know there are people who has not seen this before. So I think I hope the picture will help, and I will not bother to write the mathematical expression. Okay, so let's don't worry about the mathematical expression. Just believe me that indeed we have a bijection between n cross n and n. Okay. Now what's next? So we have a tool which says to say two infinite sets have the same size, you need a bijection. But if every time we want to show they have the same size, we have to give a bijection, it is very, very tricky, right? So for example, these things are not so obvious. So there are tools to simplify. So I guess, okay, so there's a famous theorem called the Cantor-Bernstein theorem. So let me state the theorem. Before that, I need to introduce a concept. So we know I have defined two sets have the same cardinality. They have the same size. I say there's a bijection, right? But I didn't define one set has smaller size, okay? So how do I define one set has smaller size? So I'll say this. So the size of A is less than or equal to the size of B. The correct way is the cardinality of A. But forgive me to use the word size. If there is an injection F from A to B, so I'll write the size of A less than or equal to the size of B to indicate this case. Okay. So the Cantor-Bernstein theorem says if the size of, okay, if you have an injection from A to B and you have an injection from B to A, then actually you can find a bijection. Well, that was too mathematical. We can sort of cheat a little bit, right? So you can read it like if the size of A less than or equal to the size of B, and vice versa, size of B less than or equal to the size of A, then they are of same size. Okay. So the theorem actually is much more complicated. So I will, but it's beyond our scope. So I want to say this is a tool. Suppose you can embed one set to the other and vice versa, then actually they have the same size. So this will help us a lot. For example, suppose I want to show you the interval. So the bracket stands for interval on real line. Suppose I want to convince you on real line, the open interval -1 to 1 have the same size of the closed interval -1 to 1. right? To get a bijection was troublesome. It's very hard to get a bijection. Okay, especially for us, for the general education module. But I can easily embed, sort of send this minus 1, 1. Draw it. Okay. So I want to convince you this. Okay, so I have minus 1, 1. So here I miss the endpoints. Now I have a solid interval, minus 1 and 1. I call it embed. I want to squeeze the red, match the red as part of the black. And I also want to match the black as part of red. Okay? To see the red can be viewed as part of the black is trivial because it's a subset. Because the red miss minus 1, 1. The black has more. So therefore, you just define identity. So this function is f of x equal x will send the red into the black. Right? So this is trivial. Now how about I send black back to red? Okay, so how do I do it? I'll just multiply half, right? So I'll do my g of, let's call this guy y. I'll send gy equal half of y. Okay, so minus 1 send to minus half, right? 1 send to positive half. So then you can imagine that the points in the middle, 0 send to 0. Right? 0 send to 0. So I squeeze the black things as part of the red. Okay. So then Cantor Bernstein says, if you're able to do this, you actually can match them in a perfect way. Right? So anyway, this is a useful fact. Suppose you are in mathematics. Okay. Now, finally, I can convince you the rational numbers are of the same size as natural numbers. Well, what is rational numbers? Rational numbers are ratios, right? They are quotient of two integers. So it's a over b. Now the a over b is more or less as a pair, right? Think of a over b as a pair a comma b. So a over b is more or less the same as the pairs. Right? So this picture is almost the same as that one. Right? So if you are able to do this, you are able to do that. Okay. Now, well, there are some mathematical argument, but let's don't worry about the exact argument. So the message was actually I can show the size of natural numbers is the same as the size of rational numbers. Okay. Now things are getting more and more weird, right? Because rational numbers, they are sort of dense. They are lots of elements. The integers are sparse. So if you can do this, maybe you can do everything. Maybe any two infinite sets can match each other, right? So now the question for us is, so let's define a set has strictly smaller size than the other, right? I want to define a set A is the size of A is strictly less than size of B. If if it's less than or equal to and not equal. Right? If you have an injection, but you have no surjection. Right? Now the question is, do we have examples for infinite sets? Finite sets we have. 3 is less than, ABC, the set of ABC is less than set of ABCD. Right? But for infinite set, maybe all infinite sets are they're just one size. Once you get to infinity, they can match each other, right? Well, so the specific question is, are there any infinite set having size larger than the size of natural numbers, right? So in other words, the Hilbert Hotel, would it ever have no vacancy? Maybe whatever, how many people you can collect, you can always squeeze in Hilbert Hotel, right? So you understand the question. So for infinite sets, is this just one size, or you have higher infinity? You have some small infinity, you have some bigger infinity, and so on and so forth. Well, then we have to look at real numbers. So this is Cantor's clever observation. So if the infinity is just one size, then there's no big deal, right? So Cantor will not get famous. But actually, there are lots of size of infinity. So I want to. This is in the remaining 15 minutes, I'm going to convince you that actually real number, I have more real numbers than natural numbers. Okay? So let's consider the real numbers between 0 and 1. This is an interval 0 and 1. Right? So every element between 0 and 1 can be written as in a decimal, right? So it's like 0.112 or 121 or something, right? So each number between 0 and 1 can be written in decimals, begin with 0. Okay. Now, okay, so not really an exercise. So for those who have taken CS 1231, this is an exercise. Show that these sets are of the same cardinality. Okay. Now, what Cantor did is Cantor shows the numbers between 0 and 1, the real numbers between 0 and 1, actually is more than the natural numbers. So you have a strictly larger size than natural number. Suppose you have these many guests, right? Suppose every decimal point is a guest. Then Hilbert Hotel, no matter how clever Hilbert is, he cannot arrange because there are just too many guests. No matter how he shuffle, he cannot accommodate these many guests. Okay. So how do we show this? You think that this is extremely difficult. Well, yes, it's difficult, but I can explain this to you within 5 minutes. So, okay, so this is a typical method nowadays called diagonal method, right? So let's do it step by step. So we want to show the real numbers in the interval 0, 1 cannot be matched in a perfect way with natural numbers. So in other words, I cannot list the real numbers in 0, 1 in a fashion like natural numbers, like R1, R2, R3. I want to convince you of this. Okay. Now, how do I show that you cannot list like this? So I'll say, no matter how you list them, you'll miss some number. So I'm going. So my argument is going to be like this. I want to convince you any such list. Suppose you have R1, R2, R3. As long as you have this list, it cannot be exhaustive. You'll miss some number. I'm going to show you, demonstrate a point which is inside 0, 1, but not in your list. If I can do this, I win, right? Because no matter how clever you choose your matching, you miss something. So therefore, there's more real numbers than natural numbers. Okay? Now this method is called diagonal method, and somehow it's very useful in mathematics. Okay, so let me carry out the argument. All right, so you give me a list. I want to show you miss a point. Right, this is our arrangement. Okay, so give me a list. I choose it start from instead of starting from 0, I choose it start from 1, but doesn't matter. Okay. So you give me a list R1, R2, and so these are, each of the R's is a real number. Okay. Now we already agreed any real number between 0 and 1 can be written in decimals, right? So R1 can be written as decimals. For example, R1 is this 0 dot, I don't know, maybe this is 1, 2, 3, 4 or something. So it's A11, A12, A13, and so on and so forth. So each of the A's is a digit from 0 to 9. Okay? Now R2, again, is a number between 0 and 1. So R2 will have a decimal expansion. So R2, maybe this is 0.900 or something. Okay, so it has a decimal expansion. It's something like this. Okay? Now all the way to, so you have an infinite list, so I have infinite list here. So for example, Rn is 0 dot A sub n1, A sub n2. I have to use double indices because the first index is indicating is a decimal expansion of Rn. The second index stands for the position, which digit in the decimal expansion. Okay, so I have this. Okay, so here is the information you provide to me. I want to return you a number. I want to return you a number which is in 0, 1 in the interval, but it disagrees with all of these. Right? I want to. Okay. Let me repeat my task one more time. You give me a list. I will return you a number and show that you missed the number. Okay? So this is the list you provide me. The information is written here. Now I want to return you a number, show you missed. Okay. So here's a short description. So I will do things, it's called diagonal argument. I will do things different from your number at diagonal position. Okay. So I'm going to define a number called b. So b is also have a decimal expansion. So it's 0.b1, b2, and so on. Right? So I choose my b1 depend on, okay, look at n equal 1. I choose my b1 depend on what is your a11. If your a11 is 0, my b1 is 1. If your a11 is not 0, this is the otherwise case, I'm 0. So my b11 is different from your, my b1 is different from your a11. Here, the red part. I want to choose a number as the first digit of my decimal expansion. All I need is that number is different from a11. Okay, if a11 is, what do I say? If a1 is 0, I take 1. I can take 3, I can take 4, but let's be clear, I take 1. Otherwise, I take 0. Right? If you are not 0, I'm 0. If you are 0, I'm 1. It's just to go against you, right? So this is for the first digit. Now for B2, I'll choose my second digit, which is different from A22. Because I already choose my B1, I have no chance to go against A21. But I haven't chosen my B2 yet. So I'm going to choose my B2 to diagonalize against A22. Right? Similarly, I do this for every n. So in the short form, I choose my Bn to go against your ANN. If your ANN is 0, my Bn is 1. If you are not 0, I'm 0. So just to be different from you. Okay, so is it okay? So by doing this, I get a real number. This is 0 dot something. And the real number only have 0, 1. Right? The decimal expansion only has 0 and 1. Okay? So I have a real number. I need to convince you miss this real number. In other words, this real number does not appear in your list. Okay? Why this case? I want to show that my real number is different from every number you provide me. In other words, B is not Rn for On. Is it the case? Well, how do I know my B is not R1? Well, the first digit is different. Because you see the first digit, if you are 0, I'm not 0. If you are not 0, I'm 0. So the first digit is not it's not the same. If the first digit is not the same, I have no chance. These two numbers are not equal. Okay? How do I know my B is not R2? Look at the second digit. The second digit is different. So B is not R2. So by doing the same thing, B does not appear in the list at all. So in other words, you miss B. You miss the number. Right? So this is the argument. Okay, so suppose your R1 is like this, right? R2 is like that, R3 is like this, and so on and so forth. So this is an example of saying how I get B. So if you are 0, I'm 1. If you are not 0, I'm 0. Right? If you are 0, I'm 1. If you are 0, I'm 1. Okay, so suppose here you have all zeros, and I have 1, 1, 1, 1. Right? So this is my B. Now, I want to convince you this B is from all the numbers appear on the picture. Is it true? Is B different from R1? Well, I'm repeating the argument, right? How do I convince you B is not R1? Look at the first digit. This R1 is 0, but I have 1. So it's not R1. Is B R2? Look at R2. R2 is, the second digit is 1. What is the second digit of B? It's 0. It's different. So this B is not R2. So by doing this diagonal argument, this B is different from all the numbers, all the R, Ri, Rj, so on and so forth, right? So therefore, this B is indeed missed by the list. Okay, so that's clever argument. Right? Okay, are you with me? So indeed, I spent about 5 minutes, and this is an argument by Cantor. It shows the real number really has, there's more real numbers than natural numbers. Okay, because even you look at the interval 0, 1, already have more than natural numbers. Okay, so what do we know? So we know that there's larger size than natural numbers. For example, the real numbers has larger size. Okay. Now here, Cantor not only showed there's a set has larger size than natural number. He actually showed there's no set with largest size. So the size of infinity never stop. There's no biggest size. How does he show that? He showed this funny theorem. This is called Cantor theorem. So for any set X, you look at his power set. The power set collects all the subsets, right? Remember. So let Y be the power set of X. So in other words, Y collect all the subsets of X. Y collect all the S, so that S is a subset of x. Okay, and Cantor showed the size of y is strictly bigger than the size of x. So in other words, no matter how large you give me a set, the set x, the power set of this guy is of larger size. So there's always larger size, right? So there's no largest size. Okay, the proof essentially take 5 lines, but this is the most difficult 5 lines in the whole semester. It's a very short proof. I will do this on Friday, so that when we are fresh. I don't want to do it at the very end. So allow me to continue to say some soft things, and then this thing need attention. So I'll do it next time from the very start. Okay. Okay. So suppose you believe me that Cantor has demonstrated a power set. The size of power set is bigger than the size of the original set, right? Then the corollary is logically, you know that there is no set with the largest size. Suppose there is such set, look at its power set. Well, it has larger size. So no matter what set you give me, its power set will have larger size. So there's always larger size, right? So this is the corollary from Cantor theorem. Okay, so now let's recall we have seen the size of real numbers is strictly bigger than the size of natural numbers. Okay. The question is the size of R the next size? Is there anything in between? You see, so here I have the size of natural numbers. Now I know there's something larger. Now, is this the next large thing? Can I squeeze something in between? Right? So the question is, are there any size in between? So here is the famous problems called Cantor's continuum problem, the continuum hypothesis. So the shorthand is CH. It says there's no size in between. The real number is the next large size. So there are many ways of saying that. One way of saying is this. So suppose X is an infinite subset of R, right? If X is strictly smaller than the size of R, and then it is more or less it's just the size of natural numbers. So there's nothing in between, right? If you are strictly bigger than R, then you are at most the size of natural numbers. So the answer, the continuum hypothesis says there's no size in between. The real number is the next large size. Okay. This is a famous mathematical problem. The same Hilbert, in 1900, he raised 23 problems, which sort of guide the mathematicians in the next 100 years, right? So it's called Hilbert problems. So there are 23 of them, and then this Cantor's continuum hypothesis is number 1. Is the first problem in Hilbert's list. Okay, now you would think that the question like this must have an answer, because we know real number. You learn real number in JC. You know natural number. Now the question asks some fact about real number, about natural number. It should have a definite answer, right? It's either yes or no, right? Now it turns out the situation is slightly different. It turns out it's called independent. What does it mean? So we mentioned this ZFC, right? So we mentioned that there's a collection of axioms for set theory. And also set theory is a foundation of mathematics. So some people will say set theory is mathematics. So any mathematical problem can be settled inside set theory. That's the common belief, right? Now this CH, continuum hypothesis, is different. So these two people, Gödel, we heard his name several times, and also Cohen. I'm going to show his picture in the next slide. So together they show that using set theory, using ZFC, you cannot settle. You don't know if CH is true or false. So that's a picture of Cohen. He passed away in 2007. So he got a Fields Medal because of this work. Okay, so now what? So we know that set theory cannot determine the truth of CH, right? So some people think in that case CH is meaningless because set theory is more or less mathematics. All the mathematical thinking can be formalized in set theory. Now if set theory cannot say you are true or you are false, then you are too strange, right? So some people will say that it has no truth value. Well, but many mathematicians do not think that way. So, for example, the Gödel, the same famous Gödel says ZFC doesn't settle, right? The axiom of set theory means the ZFC. So ZFC doesn't settle CH. It only means ZFC is not adequate. Right? You choose your axioms in some way. Now, these chosen axiom cannot settle CH. It means the collection is too small. You have to discover more axioms. So Gödel believed the role of CH, the continuum hypothesis, is to lead people to discover new axioms. So now people are still searching for natural axioms which settle the continuum hypothesis. Okay, so we have talked about many facts, right? And I skip lots of proofs and so on and so forth. So you may get confused. Now I want to give you a summary. So these things are, I expect you know. Okay, you don't need to know the proof, but I hope you know these as a fact. So the facts are the size of natural numbers is the same as the size of integers and rationals. Okay, for those who have taken 1, 2, 3, 1, so this is called countable sets, countably infinite set. Okay. Now, the size of real number is much bigger. So the size of real number is strictly bigger than the size of natural numbers. So this is another fact you need to know. Okay, and also I own you the proof of contour theorem, but you don't need to know the proof. You need to know that for the infinite size, there's no end. There's always larger and larger size. There's no largest infinite set because the power set is larger. So these things are what you need to know. I expect you know, right? The proofs you don't need to. I mean, CS 1231 require you to know that, but not the living with math. Okay. So on Friday I will try to finish the 5-line proof. Okay, I will give you details of the proof, and then we will talk about more counting or maybe probability. Or we will come back to really real life mathematics, not abstract infinity. Okay, I'll stop here for today.